We had the proof of the complex spectral theorem on Wednesday. Which says that a linear operator on a complex inner product space, okay, has a spectral decomposition if and only if this linear operator is normal. Okay, so right, and so now we want to develop a version of spectral decomposition for complex matrices. Okay, right. So we will say that. We let A be we say is an n times n complex matrix, right? And we define that A is called unitarily diagonalizable, okay, if there exists an n times n unitary matrix U such that D is equal to U HAU, right? So that D is a complex diagonal matrix. Okay. Okay. And so that it is equivalent to. So this is equivalent to that A can be described as U, D, U, H, okay? And we know inverse here. We know that for a unitary matrix, its inverse is just its conjugate transpose, right? So U to H is just the inverse of U, okay, for any unitary matrix. All right, so you see that actually A is diagonalizable, right? Because that we can use an invertible matrix U to diagonalize this matrix A. But it is not only diagonalizable, it can be diagonalized by a unitary matrix. So that's the reason why we call it unitarily diagonalizable. Okay, because it's unitarily diagonalizable here. Right, and so the following lemma characterize, right, unitary diagonalizability. Okay, so we will characterize that. So an n times n complex matrix A is unitarily diagonalizable, right? If and only if there exists an orthonormal eigenbasis U1, U2 up to UN for the Euclidean n-dimensional Euclidean space associated with the matrix A, where each UI in this eigenbasis is of course, is an eigenvector of A corresponding to a complex eigenvalue lambda I, okay, with lambda I not necessarily distinct. Okay. So you can see that that this is a characterization for a complex matrix to be unitarily diagonalizable. Okay, so of course it involves eigenbasis, but this eigenbasis should be also normal eigenbasis. Okay, so we see proof of that. So A is unitarily diagonalizable, right? Then this implies that there exists an n times n unitary matrix, right? You call U, and U has U1, U2 up to UN. So it has n columns. And we know that this n column, because U is unitary, so this n column forms an also normal basis for the n-dimensional Euclidean space. We know that before, right? Okay. Right, such that so we know that D is equal to UH and the A and the U, and this is lambda 1, the 2 up to lambda n. Okay, so D is diagonal, and so it has only possibly non-zero diagonal entries. So this is diagonal entries there. Okay, and this one can be so that we have AU equal to lambda 1, lambda 2 up to lambda n, and U here. Okay, so if we, oh, by the way, yep. So I think I have to multiply here. Okay, U here. Sorry, because that if you multiply U here, so if you multiply U here, okay. Now U Hermitian becomes to the identity matrix, right? And so because U is unitary, so this has become to AU, and you have U there. Okay. All right, and so we can represent the matrix by using columns. One, lambda 2, lambda n. no battery. Okay. All right. And so if you multiply this matrix with that, you look at this as a row of column vectors. Okay. So you multiply this column vector with you multiply this row vector with this column vectors, you find that you have lambda 1, u1, lambda 2, u2 up to lambda n, un. Okay, we have that. So that implies a ui equal to lambda I ui for I from 1 to n. So that is Eigen Equations. So this implies that ui is an eigenvector of A corresponding to eigenvalue lambda I. Okay? Right, so each ui is an eigenvector of A corresponding to eigenvalue I. And as I just mentioned that u1, u2 up to un is an orthonormal, is an also normal basis for Cn. Okay? We know that. So that is an orthonormal basis, and every basis vector is an eigenvector of A, right? So that u1, u2 up to un is an orthonormal eigenbasis for Cn associated with the matrix A. Okay. So that is the parts here. So we have an orthonormal eigenbasis, right? And each ui is an eigenvector of A corresponding to eigenvalue lambda I here. All right, and so we have the forward part. How about the backward part? Well, so that we know we have orthonormal eigenbasis. First of all, this one is an eigenbasis, right, for Cn. Okay, we know A ui equal to lambda I ui for all I from 1 to n. Right. So from this data, we know this information. So this is an eigenbasis and have these Eigen Equations. All right. And so from there, so we can write down all these eigen, we're just doing the things big word, right? So we write down this n eigen equation together. So this is AU1, U2 up to AUN. This is number 1, U1, number 2, U2, number n, UN. And this is becomes to U1, U2 up to UN. And we have other matrix like this one. Okay. All right, and we define this as an U here, so that it U here. Okay, so we have a U equal to U and the D here. All right, so where U is U1, U2, UN is unitary, since the columns is an orthonormal set. Okay, so it's unitary because that the columns is an orthonormal set. Okay, so we use the information here is an orthonormal set. Okay, so that U is unitary, and D it's and it's a diagonal, a complex diagonal matrix. Okay. Okay, and so if we multiply both sides by U Hermitian, so we multiply U Hermitian here. Okay. So now U Hermitian U is equal to identity. So we have D equal to U Hermitian AU. Okay. And here D is diagonal matrix. U is unitary matrix. So that A is unitarily. It's unitarily diagonalizable. Okay. All right, so we complete the proof here. All right. So that is the is this lemma here. All right. So now if an n times n matrix A, right, is unitarily diagonalizable, okay, then we know A is equal to U D and UH. Okay, so we know A has this decomposition, okay, with U unitary and D diagonal, right? So that we look at AHA. So we multiply the conjugate transpose of A with A itself. Okay, and so we have U, D, UH, HA, and here U, D, UH. Okay, so we just plug in this decomposition here, and so we have U, D, H, and the UH, U, D, UH. Now, this product is identity, so we have U, DH and the D and the UH. Right, now, because D is diagonal, so D to H is also diagonal. You just change the diagonal entries by their complex conjugate, right? So that you have D, so you can exchange them, okay? So the multiplication of two diagonal matrices, right, is commutable. You can exchange the order because they are diagonal. In general, the multiplication of two matrices is not commutable in general. Right? But for diagonal matrices, you can exchange the order of multiplication. Okay? All right, and so then we can go to the reverse direction. And so you have, so we have U and the D and U, H, U, D, H, and the U, H. Okay? Okay, so we insert this identity matrix. And now we go back to here. We have U, D, U, H, and U, D, U, H, H here. Okay? And this is A and AH. Okay. Yep. This one? Oh. Oh, because when you take the Hermitian conjugate, you have to take the Hermitian conjugate H1, but you have to reverse the order of multiplication. You know that if you have two matrices, okay, just like H, so this is A, B, you take the transpose, right? Here. And so you have A, B, you take the transpose. And when you take transpose inside it, you have to take here, reverse order, yeah. Okay. And so that you have, you have BA, and this is BA. Then you have BH and AH. I'm sorry. Yeah. So you have to. Other questions? Okay. So we just established that these two are equal, right? So they are equal. So this implies that AH A equal to AAH, i.e. A is normal. Okay. So we have a conclusion that if A is unitarily diagonalizable, then this matrix A is a normal matrix. A normal matrix we defined before, right? So it means that AHA equal to AAH. Okay. Right, so this is a necessary condition if A is the unitary diagonalizable. But the next theorem tells us that it's also sufficient. So n times n complex matrix A, it's unitarily diagonalizable if and only if, all right, A is normal. Okay, if only A is normal. And the proof right? The forward direction that A is normal is a necessary condition has been proved here already. Okay, so this is done in above. All right. How about the backward direction? Well, so we consider the linear operator T x AX on Cn. Okay. So we consider the linear operator defined by this matrix A. Okay, so it's a linear operator on this n-dimensional Euclidean space. Okay, and we know that I think in a previous example, A is normal if and only if T is normal, right? So we illustrate that this linear operator is normal if only A is normal. Okay, we already discussed that before, so I don't want to repeat it again. All right, and because T is normal, okay, so now we can apply. So we can use the complex spectral theorem, right? So by the complex spectral theorem, there exist complex numbers. Okay, lambda 1, lambda 2 up to lambda n, not necessarily distinct, right? And also normal basis U1, U2 up to UN for Cn, such that we have the spectral decomposition. Okay, right. So this is the result of the complex spectral theorem. So we have this is spectral decomposition. Okay. So in particular, right? If you that x equal to the basis vector ui, so uj, when you put into that, then you find that which is lambda j, uj, because that ui's are also normal to each other. Okay, so that's implied that uj is an eigen and also you know this is equal to also a uj. Okay, so by this definition, so we know this is auj. So auj is equal to lambda j uj. So uj is an eigenvector of a, okay, corresponding to eigenvalue lambda j, okay, for all j from 1 to n. Okay, so basically we establish Eigen equations here from the spectral decomposition, decomposition. Okay, and so the conclusion is that U1, U2 up to UN, okay, is an orthonormal eigenbasis for Cn, okay, associated with A. Okay, and so by lemma, we have characterized this before by lemma A.1 point C here, right? A is unitarily diagonalizable, and we have done. So we complete the proof here. So that so we have this representation. Okay. Questions? All right. Now we have to go to answer the real case. In our discussion on Wednesday, we know that if a linear operator on a real inner product space, real finite dimension inner product space, has spectral decomposition, then this linear operator should be self-adjoint. Okay? So for real case, a linear operator has spectral decomposition, then this linear operator must be self-adjoint. Okay? And so we have to prove it is also sufficient. Right? So we have to show that if a linear operator on a real finite dimensional inner product space, if it is self-adjoint, then it has a spectral decomposition. But before we can do that, we have to show that every self-adjoint linear operator has real eigenvalues. We haven't answered this before. Okay. So but we do that first for matrices. All right. Okay. So now the statement is that any n by n self-adjoint matrix A over F. All right. So this self-adjoint matrix can be complex or real. Okay, just self-adjoint. So we know if A is complex, then self-adjoint means Hermitian. For the real case, self-adjoint means symmetric. Right. So you have to know that because we defined that carefully. Okay, before. So that and here, so any n by n self-adjoint matrix A over X actually has n real eigenvalues. And but where multiplicity, right, is counted. Right. So we just counted its multiplicity. Means that the meaning of this statement says that the characteristic polynomial of any self-adjoint matrix can be split into linear factors. Okay? So we know because this is n times a matrix, so its characteristic polynomial is a polynomial of degree n. So it will factorize to n linear factors. Okay? To n linear factors. And each factor has root, which are real numbers. Okay? So we call real eigenvalues. Yeah. And the linear factors can be repeated. Okay? So we have multiplicity. Okay? So it's possible that these unreal eigenvalues are all the same. It's possible. This is the extreme case. The other possibility is that these unreal eigenvalues are all distinct. So we have n distinct real eigenvalues. So that there are all possibilities here. Okay, but the idea is here. All right, so, and this theorem is crucial for us to prove the real spectral theorem. Okay, so let me address that. Right? And the idea for the proof is that we're regarding a real matrix. Right? So we're regarding a real matrix as a complex matrix. First. Okay? So first we regard a real matrix as a complex matrix. Okay? So in this situation, then a real self-adjoint matrix A, right, is a complex self-adjoint matrix. Okay, since A H is AT is equal to A. Okay. All right, and so such a complex self-adjoint matrix A is Hermitian. Okay, so it's Hermitian. Right, so that it is normal. Okay, so Hermitian matrix implies that it is normal. All right, and so by the previous theorem, so by theorem A.1.I. Okay, and the lemma A.1.C before. Okay, A has n eigenvalues. All right, so and A has n eigenvalues: lambda 1, lambda 2, lambda n in C. Right, because we regard this real matrix as, anyway, just regard A as a complex matrix. So this theorem and the lemma can only tell us that it has n eigenvalues in C. Okay, in C. Okay, in C here, and not necessarily distinct, okay, as we know. Okay. Now we can apply corollary 8.1.1 plus 2. In that corollary, it says that if a self-adjoint linear operator has an eigenvalue, then this eigenvalue must be real. Okay? This corollary just say if a self-adjoint operator has an eigenvalue, then this eigenvalue must be real. But this corollary does not say that a self-adjoint matrix has eigenvalue. Okay? It doesn't say so, right? But here, we know it has eigenvalue. All right? And so, by corollary 8.1.1 plus 2, with the f equal to c in the complex case, this n eigenvalues, lambda 1, lambda 2, up to lambda n, must be real. Okay? So now we are affirmative that any n by n self-adjoint matrix A over F, no matter is real or complex, right? If it is self-adjoint, then it will have n real eigenvalues. Okay? At least means that at least one eigenvalue, right? That is what we want. Okay. All right, so now we are able to state the real spectral theorem. Okay. Right. Okay. So T, a linear operator on an n-dimensional real inner product space. Okay? So we are considering real case. So they are real numbers. Lambda 1, lambda 2, up to lambda n. Not necessarily distinct. And also no more basis U1, U2, up to Un for the real Euclidean space Rn. Oh, no, for V, I'm sorry, for V, sorry, for the real inner product space, such that Tx, so that it has spectral decomposition, lambda I, x, ui for all x in V, right? So we have a spectral decomposition if and only if T is self-adjoint. Okay, so if T is self-adjoint. All right, now this derivation has been done. So this is done before in the in our previous discussion. Okay, so we only need to prove the reverse direction to show that this is also sufficient. Okay. Right. So this is saying that this is going to, maybe I name that the spectral decomposition as 2. Okay. Also, so we will prove 2 by induction on the dimension of V. Okay, so this is pretty much similar to the proof for the complex spectral theorem, but I will make the points which are different from the complex case clear here. Okay, so for MS for n equal to 1, again we let U, okay, be an orthonormal basis for V. Now again, since TU is in V, TU must be equal to lambda U, because that the V is spanned by U only, right? So for some real lambda. Okay, so we have that, and we will call it as U1. Okay, so we have U1 here, and U1 lambda 1 U1. Okay, so some real lambda 1. All right, and since x is equal to x U1 for all x in V, we have Tx equal to T x U1. So this is x U1, T U1. And by this Eigen equation, we have lambda 1 x U1, which is 2 with n equal to 1. Okay, so we prove the spectral decomposition when the dimension of V is 1. Okay. So this is the same as before. Okay, and so we assume that 2 is true for n equal to 1 to up to k, right, with k greater than equal to 1. Okay, and so now we consider n equal to k plus 1. Okay, now by theorem 8.1.f and theorem 8.1.j. Oh, maybe I haven't corrected. So I have to say Yeah, that's correct. 8.1.f says that they have the eigen value. So we have a matrix representation. Okay. We have a matrix representation. Okay. So that the linear operator and its matrix representation will have the same eigenvalues. Okay. And from the J here, the T has at least one real eigenvalue, lambda. Okay, so that is crucial. Because in the complex case, that we use the fundamental theorem of algebra to make sure that that every linear operator has at least one eigenvalue. Okay, because that its characteristic polynomial will split into linear factors. Okay, so that is, so we apply a very powerful tool called the fundamental theorem of algebra. But we cannot apply this powerful theorem for the real case. Why? Because our characteristic polynomial has real coefficients. And we know, for example, x squared plus 1, this polynomial cannot split into linear factors over real numbers. You can't. Okay, so that is the difficulty when we deal with the real case, right? So that's why we have to build the machinery and finally use this theorem saying that we have a self-adjoint, so that if T is self-adjoint, then if we choose an orthonormal basis, its matrix representation is also self-adjoint, right? This is the theorem 8.1.f tell us. Okay, so you have to select an orthonormal basis, and relative to this orthonormal basis, a self-adjoint linear operator has a matrix representation which is also self-adjoint. And once its matrix representation is self-adjoint, then we can apply theorem 8.1.j here. Okay, for a self-adjoint matrix A, we have unreal eigenvalues. Okay, and so that means that T has n eigenvalues, but you have to count the multiplicity. At least we know it has one real eigenvalue. That is enough. Okay, so this is the crucial point. I have to point it out. Okay, and the rest of the proof. So the rest of the proof is similar to the proof of the complex spectral theorem. All right, so I don't need to repeat it. Okay, here. You can see, look at my lecture now, you can see that exactly the same idea. Okay, exactly the same idea. All right, so, okay, so anyway, so we have proved the situation here. Okay, and I think we take a short break for 5 minutes. You can take a rest. And because today, yeah, you can free to go to the restroom. I just want to know you because you are students joined with me in the last lecture. Very special to me, right? So I want to know you. It's not to say mean anything, but mean something extra. For example, in the future, if you want my reference later, then I will consider that significantly. Any student not in here right now, I may reject them. Okay, so I want to know you. Okay, you know, write reference data is not an easy job, right? I have taken my time. Okay. Okay, so because not many of you can go freely, okay? All right, so I just name your name here and let me know you here. Okay, Chinese name, I can pronounce that exactly, but maybe sometimes I make either, but if you have foreign name, then just forgive me if I pronounce that in correct way. Okay, so Mr. Sao Weida, not here? Okay, great. Mr. Liu Yichen. All right, Mr. Gideon Levy? No. Mr. David Jacob Pinko? No. All right, Miss Olivia Gusmo-Putri? No. Mr. Matthew Singhi, not here. Mr. Kenneth Egger, not here. Wow. Mr. Fernando Michael, no. Mr. Dario Prayogi, not here. Miss Ho Nong Fen, not here. Mr. Chama Kikoku. All right. Okay. Mr. Lee Yongjin. No. Mr. Yuan Da. Not here. Miss Wang Yixuan. No. Mr. Liang Haojun. Okay. I know you. Good. I see you quite often. Miss Xie Yunzhen, no. Mr. Cai Rui Qian, not here. Miss Yu Caisan, no. Miss Liang Jinru, no. Miss Song Ziying. Mr. Cai Weichen, Miss Cai Peiyu, thank you. Miss Wang Yihui, right? Mr. Liang Yuan, okay, great. Then I know you. I can match the name, okay. Mr. Qin Wenfeng, Mr. Qin Si Wang, no, okay. Mr. Wu Yanjie, Mr. Xu Junmao, Mr. Yang Shixian, good, okay, see you, great. Okay, Mr. Cheng Jinzhong, yeah, Mr. Shao Yentong, no. Mr. Xu Shengqi, okay, Mr. Yang Ruiqi, Mr. Zhuang Ziyu, Mr. Chen Wenqi, oh, thank you, Chen Wenqi. Am I right? Wenqi, right? Thank you. Mr. Chen Yanqi, okay. Mr. Hong Jinghe, no. Miss Zhang Qizhen, okay. Mr. Lin Yongzhong, Yongzhong, right? Okay, good. Yongzhong. Mr. Wang Weixin, no. Miss Ongo Washito, Mr. Ongo Washito, no. Mr. Wang Xinxiang, oh, thank you. Mr. Xie Zhonghan, Mr. Zhang Jingzhe, Mr. Guo Changwei, no? Mr. Wu Shixuan, Mr. He Guanxian, no? Mr. Cheng Pinzhong, Mr. Zhang Chongling. Oh, I'm sorry, Miss. Okay. Sorry about that. Oh, it's a big mistake. I'm really sorry. Really, I'm really sorry for that. Sorry about that. Such a kind lady there, but I'm sorry. I'm sorry. Okay. It's so embarrassing, you know, sometimes. Yeah. Okay, Mr. Cheng Lizhong. Oh, okay, thank you. Okay. Miss Liao Ziyu. Okay. Miss Cheng Jiaying. Okay. Oh, I'm sorry, Huang Jiayin. I'm sorry. Once again, one mistake. I'm sorry. Okay, yeah, Jiayin. Thank you. Miss Fu Xiaotong. Okay. Mr. Cheng Chuwen. Mr. Jian Yuquan. Mr. Yu Junyue. Oh, Junyue. Okay. Junyue. Good. Well, I guess Miss Huang Yufei, I think it's she, right? She, not he. He. Wow, Mr. Huang Yufei. Sorry. Okay, yeah, another mistake. Miss Yang Enxuan, no. Mr. Timothy Marville. Miss Zhao Yiqi, Miss Tang Yongxuan, Miss Nai Ziyun, okay. Mr. Qiu Yongning, Miss Li Peiyuan, okay. Okay. Miss Jian Yening. All right. Good. Thank you. If you want my reference, don't worry about your grade. I will try my best. Okay. Okay. So once we finish the real spectral theorem, okay, we will say one thing, okay. So an n times n real matrix A is called, so this time for real matrix, we will call orthogonally diagonalizable. Okay, if there exists an n times n orthogonal, right? Orthogonal real matrix U such that D is equal to U transpose A, U is a real diagonal matrix. Okay, so you can compare the statement with the complex case. The only change is that I change the unitarily to orthogonally. Why? Because that we asked to use the real orthogonal matrix, not complex unitary matrix here, right? So to have that, okay. So that is the situation, all right. And so we will have some similar lemma and the theorem. Okay, so now we use lemma A.1.D to characterize that orthogonal diagonalizability, right, of a matrix. So an n times n real matrix A is orthogonally diagonalizable, all right, if only if there exists an also normal eigenbasis U1, U2 up to Un for the real Euclidean space N associated with the real matrix A, and where each UI, okay, is an eigen vector of A corresponding to real a real eigenvalue lambda I, with lambda i's not necessarily distinct. Okay, so this characterization is basically the same as the complex case, you know, but everything should be real. For example, you have to have real eigenvalues, okay? You have to have real eigenvalues to use. And so the proof will be, so I would like you please see the lecture notes, right? Because the idea would be parallel to the complex case, right? So it's not necessary for me to repeat it here, okay? And so, so by the way, yep, this is in the part 2, right? I sent you this morning, so if you can download it from the website. Okay, now so if an n times n real matrix A is orthogonally diagonalizable, right? Then we know A can be written as U, D, U, T. Okay, so with U, a real orthogonal matrix, and D, a real diagonal matrix. Okay, so that the transpose of A, so we look at the transpose of A, and it's U, D, U, T transpose. Now when you take transpose inside the parentheses, then you have U, T, T, D, T, and the ut. But utt is u, and the dt is d. Why? Because d is diagonal. So the transpose of a diagonal matrix also is itself. And this is ut. And what? This is A. So you can see that if a real matrix A is orthogonally diagonalizable, then this matrix A must be symmetric. This is a necessary condition. Okay, so now we have a version of real spectral decomposition for real matrices. So n times n real matrix A is orthogonally diagonalizable. All right. Orthogonally, this is called the spectral decomposition. Okay. Even though we use the orthogonally diagonalizable to describe this situation. Okay, so it is orthogonally diagonalizable if only if, all right, A is symmetric. Okay, so that means, so this is very strong theorem. So if a real matrix is not symmetric, then this matrix cannot be orthogonally diagonalizable. All right, no hope, impossible. All right, so it's a very strong theorem. Okay, and the many textbooks does not mention this point at all. Okay, that is pitiful. But this is crucial because in many situations we use the real case. For example, in machine learning or in big data analysis, the data you handle are all real data. So you have to deal with the real matrices. Okay, and in that case, if you need something about the spectral decomposition of a real matrix, you have to make sure the matrix is symmetric. But for complex case, then you can relax that. The matrix can be only normal will be enough. Okay. All right. So the proof, and so the proof again, I will leave you to my lecture note. All right. Okay. So. So I will save the time for at least 2 topics, so that okay, I have to change part 2. Okay. All right, so I will discuss briefly the Cayley-Hamilton theorem. Right? So the Cayley-Hamilton theorem, so we are a little bit leave inner product space a while. Okay, so we consider a linear operator, okay, on a vector space, so only vector space. Okay, so this theorem is good for linear operator. Please. Diagonalizable, hey? Oh, by definition, okay. So we say a real matrix is orthogonally diagonalizable if we can find an orthogonal real matrix U such that we can use U to diagonalize A. Okay, and so if this is true, this is the same as A can be written as U d U t. Okay, and because U is orthogonal, so U transpose is just its inverse. So you have U d U inverse again, right? So it just means that you can diagonalize this real matrix, but not only use invertible matrix to diagonalize that, you have the chance to use an orthogonal matrix. Okay, so that is called orthogonally diagonalizable. Yeah, it's here. Sorry, no problem. All right. Okay, so actually, this is people say that this is spectra decomposition of A. Okay, so we'll call this this spectral decomposition of A. Why? Because the diagonal matrix contains eigenvalues there, and the U, the orthogonal matrix, contains eigenvectors there. Okay, and also they are not only eigenvectors. This eigenvector form an orthonormal basis. Okay, so it's much more stronger. Right? So that's why we call this a spectral decomposition of A. This formula itself. Okay, so if you so this is spectral decomposition, and so the theorem can be regarded as the real spectral theorem for the spectral theorem for real matrices. Okay, because it says that the only possibility to have this property, right, if only if A is symmetrical. Okay, other questions? Okay, all right. So the Kelly-Hamilton theorem says, so suppose T is a linear operator on a vector space, V over F. F can be R or C. Now for all K, K is an integer. Okay, then the K-fold composite of T. So we do the composition K times. So we use K copies of T to do the composition. Okay, and so the K-fold composite of T, okay, will be denoted as T to the Kth power. Okay, and we define T0 to be the identity operator. Right? So the zeroth power of T is just by definition is the identity operator. Okay? All right, and so a linear combination. So if we take a linear combination of the T case, okay? Right, so maybe the coefficient is P0. Right? All right, so we can form a linear combination of linear operators because each t, the case power is a linear operator again, right? And so the linear combination of linear operators is also a linear operator, okay, on the same vector space V. And so this linear combination will be denoted as f of t. Here, the polynomial will be b0, b1t plus bn/tn. Okay. So this linear combination, linear operator, is regarded as you substitute the indeterminate t in this polynomial by the linear operator t there. So we call this as f of t here. All right? So every time when you think of to see that if a polynomial of t here, it means that it's a linear combination of a k-fold composite of t. All right? And from the 0th fold up to the nth fold. Okay. And each, for example, the n fold is a composition of n copies of t. Okay, so you do the composition. Okay, right. Okay, and so with this understanding, so with this understanding, I will state the Kelly-Hamilton theorem directly, even though it cost several pages to develop it in my lecture notes. Okay, so all right, so T is a linear operator on a finite dimensional vector space over F, and F lambda, the characteristic polynomial of T. Okay, so we have a characteristic polynomial of T. Then if we evaluate the characteristic polynomial at T, so that means that we form a linear combination of the T's power. Okay, we form a linear by using the coefficient as the characteristic polynomial. Okay, so if we do the substitution, okay, then this linear operator is the zero linear operator. Okay, so 0 means the zero operator. Right? So that is, we say that T satisfies its own characteristic equation. Or Eigen equation, but yeah, characteristic equation. Okay, this is called the Kelly-Hamilton theorem. All right. All right, so I have spent some pages to develop a proof for this theorem, okay? And it's a good preparation if you want to study the Jordan form, right, for general matrix. All right, and so this material would be quite useful, okay? Yeah. Initially, I have the ambition to write down Jordan form materials, but that would be quite intensive for you in this semester, okay? And so anyway, so I want to save some time to go to the next section about the matrix factorization. There are a lot of matrix factorization. Okay, we mentioned some of them before. For example, this is the matrix factorization already. A can be factorized into product of three matrices here, right? Right. In terms of the spectral decomposition. Right. So this spectral decomposition is very special, right? It's only for real case, for real matrices, this is only for what? Symmetric matrices. Because we require this matrix U should be orthogonal matrix. And this D should be real diagonal matrix. Okay. Now for the, I erased that. For the complex case, we know if a complex matrix A is normal, then it also has the similar representation. We call it unitary diagonalizable, right? That means that in that case, if A is complex case, we know A can be written as. So if A is normal, then we can find a unitary matrix U, and we can find a complex diagonal matrix D, such that A can be factorized in this way. So we already know the matrix factorization for some special types of matrices already. Okay? And so the purpose of this section is to develop, yes, please. Mm-hmm. For example, you know, characteristic equation is that this is the characteristic equation, right? We use the characteristic equation to find the eigenvalues. That's correct, right? And so every eigenvalue satisfies the characteristic equation. Okay. And here, because we just evaluate the value of f at with a linear operator. Okay. Now, and then we find that this comes to the zero operator. So we regard the zero as the zero, right? But it's an operator, it's not a number zero. Okay. So we will say that, yeah, it is satisfied. Okay. But I quoted because it's similar to saying so. Yeah. And the correct interpretation of this symbol is here. If it is that this is actually by our definition. This is by definition, right? So f of t means that a linear combination of the tth power, right? The linear combination, and the tth power is just the k4 composite of t. They are compositions of linear operators. Okay, so each one is a linear operator, and you do the linear combination. So this is a linear operator. Okay, and the Kelly-Hamilton theorem says that if this f of t is happen to be the characteristic polynomial, if if ft is the characteristic of t, then this evaluation becomes to the zero operator. Okay, and in the, I think that it would be in 19th century or not. Hamilton or Kelly discovered this fact, and I think he wrote a data to a friend, say, I discovered a fundamental result about the matrices. Okay, just because this is a genius discovery, you know, it's not at all trivial. Okay, you think about more than 100 years ago, right? So, so that this is just a kind of a verbal description of this situation, right? But the exact meaning, you have to interpret what the meaning of this symbol. Okay, it just means linear combinations of t's power. Okay, and every t's power is just k4, the composite of the same linear operator. Okay. All right, so indeed there are many different useful matrix factorizations for different class of matrices. Unfortunately, we have time limitations. So in the rest of the time, I would like to give you the single value decomposition, a very important decomposition nowadays. Very important, you know, in many disciplines. For example, in data analysis or in machine learning field, that SVM is very important to us to understand a lot of different algorithms and results. All right, so I think I will directly go to Reddit. All right, so actually I wrote a subsection about positive and the non-negative definite matrices. All right, and the non-negative definite matrices, I have asked you to do homework, additional homeworks, right? Because so I decided to give you a little bit more discussion about these topics in the lecture notes. So I developed some of the results for you to see. All right, and so please see the lecture notes. All right. Okay, and so there are more results about positive and non-negative definite matrices, and I prove necessary and sufficient condition for a matrix to be positive or negative definite. All right, some necessary sufficient conditions for that. Okay. All right, so okay. So now this is so I want to explain okay. All right, so I try my best to explain that this result. Okay, so so we deal with rectangular matrix. All right, can be real or complex. So this decomposition is for rectangular matrix, not only for square matrix. So that's why it's so useful. Okay, and this decomposition is very similar to the spectral decomposition for square matrices. And the significance for this decomposition is that because for the spectral decomposition, you are required normality for complex case. You are required for symmetry for the real case. So both are strong conditions. But here, the single variable decomposition, why it's so important? It's because that this decomposition is true for every m times m matrices. No more restrictions. Very, very general. Okay? Very, very general for that. And the decomposition is very similar to spectral decomposition. Okay? So this is the reason why it's so important. All right. And we know HA, okay. All right, so I confirm myself to a complex case. Okay, but in my lecture notes, I do it real complex in parallel, simultaneously most of the time. Okay, so that this one, or sometimes you say AT, okay, when F is equal to R, right? Okay, we know that this is N. All right, so this is M times N. Now, we take the complex conjugate transpose away, so this is become N times M, and this is M times N. So together, it's an N times N matrix. Okay, and there is also N times N non-negative definite matrix. Okay, so it's non-negative NON non-negative definite matrix. All right, for the complex case, and it becomes to real symmetric, and becomes to symmetric non-negative definite matrix. Okay, so I think that would be the recommended exercise number 15. I think so. I mentioned that if you have a real non-negative definite matrix, it may not be symmetrical. Okay, it may not be symmetrical, but the ATT together is symmetrical, and it's also non-negative definite. Okay, for the complex case, this of course this is a Hermitian, all right, and it's also negative definite matrix. The reason why I do not put the Hermitian here is because that in the recommended exercise 15, I ask you to prove that if we have a complex non-negative definite matrix, then this matrix must be Hermitian. Right? I ask you to prove that. Okay? So it's not necessary to put Hermitian here. Okay? For the complex case. But for the real case, you need to put a symmetric case here. All right, so now this is what you have, right? And so now we have proved the complex structure theorem and real structure theorem, right? Already. So by theorem A.1.I and the lemma A.1.C for the complex case, and by theorem A.1.L and the lemma A.1.D when for the real case. Okay? There exists an orthonormal eigenbasis V1, V2 up to Vn for Fn, okay, associated with the matrix AHA or ATA for the real case. Okay. And where Vi is an eigenvector of AHA corresponding to eigenvalues lambda I. Oh, not only going to non-negative. Okay, non-negative eigenvalues. Okay, and the eigenvalues are non-negative because in the recommended exercise number 15, I asked you to prove that, right? For any non-negative definite matrix, if it has eigenvalues, then this eigen must be non-negative. Okay, so we have non-negative eigenvalues, eigenvalue lambda I with lambda i's not necessarily distinct. Okay. Okay, so I think I have a typo here. Please correct it. I write plural form. This is incorrect. Okay. Okay. So Vi corresponding to lambda I. Okay. So okay. So please delete this later S here. Okay, and so that is from our spectral decomposition, or our spectral theorems before we developed. Okay, so we know AH, A, Vi is equal to lambda I, Vi. Okay, so this is what we get. Okay, so even though A is arbitrary, right? Arbitrary M times M matrix, but when you form such a matrix, then this matrix is very well, right? It has nice property. Okay, so we know that it is non-negative definite, okay, in general, and for the real case, it's a symmetric, okay, non-negative definite. So by spectral theorems, there exists an orthonormal eigenbasis, right? Orthonormal eigenbasis. A lot of information here associated with this matrix. Okay, right. So under the eigenvalues are non-negative, also important. Okay, and we have this Eigen equation, right? Okay, so that is the basics. So we have a solid background to study single value decomposition. Okay. Okay, so this information has been obtained immediately from our previous spectral theorems there. Okay, so for our convenience, by reindexing, if necessary, all right? So we assume that we have order for the eigenvalues. Okay. All right. So suppose lambda 1 is the biggest eigenvalue. Lambda 1, up to lambda r, they are all positive. And then the next one is 0. Okay, so we may have some 0 eigenvalues there. Okay, so this is just for our convenience. Okay, we can do that, right? We can reindexing the eigenvectors and eigenvalues, right, to get this result. Okay. All right. Now, since the eigenspace corresponding to eigenvalue 0 of the matrix AHA, if exists, okay, is just the null space of AHA, right? Because you the Eigen equation for the Eigen equation corresponding to 0 eigenvalue is this matrix equation, right? And which is just 0. So you are solving homogeneous linear system. That's why the solution space, the null space, is just the eigenspace corresponding to eigenvalue 0. Okay, so this is the 0. And so that n minus r is the, so how many, so that because they are eigen, so u r plus 1 up to u, vr plus 1 up to vn. Okay, so corresponding to 0. So they are all in, so from the Eigen equations here, if I is, so when, so from here, right here. So when I make a remark here, for we know AHA is equal to 0. Okay, so that they are in the null space. Okay, and the all other vi for I from 1 to r, right, is not in the null space, because so, and for which is not the 0 vector. Okay, so vi from I from 1 to r they are not in the null space. But Vi for I from r plus 1 to n, they are in the null space. Okay. So you can see that MSR is the nullity, is the rank, is the dimension of the null space. So it's the nullity of AHA. And so that R is equal to n minus MSR is equal to the rank of the AHA by the nullity rank theorem of the matrix. Okay, so that is in chapter 3. Okay, in chapter 3. So the R is just the rank of this positive non-negative definite matrix here. All right, so this is our understanding for that. So any questions for the statement here? Okay. Okay. Now everything up to now is about AHA, right? But we are concerning A. This is our purpose, is A, not this derived matrix. Okay, so we have to know the action. So now the action of A on the, so we want to know the action on the orthonormal eigenbasis Vi of with AHA. All right, so we now look at the action. Now the action has the following effect. We look at A, Vi. So this is the action, right? A multiplied with Vi. And we look at, we take the inner product. Right? So the action will be AV1, AV1, AV2, AV3, actually up to AVN. Right? This is the action of A on this basis. And we look at we are trying to see their inner product. And this is actually Vi and the AHA Vj. Okay? Because AH is the adjoint of A. Okay? So when we move this matrix to there, we have to replace A by the adjoint of A. But the adjoint of A is AH. Okay? Right? So we have that. And now Vj is an eigenvector of this matrix. So that this is Vi, and we have a lambda j Vj. Okay? Now, you move out the lambda j, but lambda j is real because it's non-negative, right? So it's real. So you can move it out. If you take the complex conjugate, you will not change it. So you have Vi and Vj. And this is delta Ij. So that means that they are orthogonal to each other. Okay? So which implies all right, so which implies that the AVI, this is say is an orthogonal and the index say of vectors in Fm. They are now in Fm, not Fn. Why? Because you do the action, right? because the matrix m times n, even though all these matrices are n times 1, okay, they are n-dimensional column vectors. But when you multiply Vi by the matrix A, the result is m-dimensional vectors. So you have an orthogonal index set of vectors in there. Why we say that it's an index set? Because some of the components may be the same. Okay, may be the same. Why? You will see immediately why. Okay, so we know that they are orthogonal index set of vectors, and if I equal to j, we have the square of the length of AVI. All right, this is if I equal to j, this inner product is just the square of the length of AVI, which is equal to lambda I. Okay, which is equal to lambda I. We know that. But look at here. When I is in between r plus 1 up to n, it's 0. So that means that this vector is a 0 vector. So in this orthogonal index set, a lot of vectors are 0 vectors. Okay, that's why we call it index set. We use index. Because only index set can have the same members there. All right? All right, and so suppose this is called 3. So that, so by 3, AVI, now we restrict I from 1 to R. Okay? I from 1 to R. We find that if I is from 1 to R, then the length is non-zero. Okay? And so that this vector is a non-zero vector. Right. So now this one is an orthogonal set. Orthogonal set of non-zero vectors. Okay. And right. So this set is an orthogonal set of non-zero vectors. Maybe I'll see in Fm and the span, right, spans the column space. Okay? Spans the column space of A. Why? Things, right? So the column space of A, by definition, is AX. So this is the definition of column space, right? And this is A of and every vector in the n-dimensional Euclidean space can be written as the linear combination, right, of the basis here, right? Because Vi is a basis, right, of Fn. So you have that. And so this is summation. Okay. But as we know, if I is from r plus 1 up to n, AVI are zeros. Okay, are zeros. So this implies that. So from here, we know A. Okay, so when I is in between r plus 1 and n, AVI is the 0 vector. And so you can just write down AVI. And alpha I will be enough. And so this is the span of AV1 up to AVR. Okay, is that okay? So from here you can see that this set span the column space of A. And this set is orthogonal set of non-zero vectors, so that this implies linearly independent by Theorem 7.1.2. Yeah, right? So a orthogonal set of non-zero vector implies that it is a linearly independent set. So now this is a linearly independent set and also span the column space. So what is the conclusion? The conclusion is that the conclusion is that the columns. The conclusion is that so that the AVI I from 1 to R is a basis. So it's or is an orthogonal. All right, orthogonal basis. So it's an orthogonal basis for the column space of A. Okay, so now you have something, right, related to A gradually, right? We just do it step by step. Because originally, what we have are just the eigenvectors and eigenvalues of which matrix? AHA, not A. Okay? Not A, is AHA. But our concern is A. And so now we find that when we take the actions on the also normal eigenbasis here, we find that we can have an orthogonal basis for the column space of A. Okay, and so that's R is the rank of A. Okay, but R is the rank of AH. So we prove that the rank of AHA. Okay, so the same. So we have a byproduct to show that the rank of AHA is the same as the rank of A. Okay, and this is the R here. And also we note that the VI R plus 1 and okay, the span, the null space Okay? You spend the null space here, right? You can see from this equation the null space of A. Okay? So maybe I'll say that since, maybe I write it, since A, V, I equal to the 0 vector for all I from 1. Okay? So this is say spans the null space of A. Okay? And then AHA and the A have the same null space. Okay, so actually we have a lot of information. Okay, so we know HA and A have the same, exactly the same null space. Okay, and AHA has the same rank. They have common property there. Okay, and we also find an orthogonal basis for the count space of A. Okay, so all these are the data we have. So now, okay, now we can turn this orthogonal basis, orthogonal set into orthonormal set by normalize each vectors there. Okay, and we know that the length of AVI is the square root of AI, of the lambda I here, right? Because here, so that now that's A V1 lambda 1, A V2 square root lambda 2 up to A VR square root lambda R is an also normal set. In FM, okay, and can be extended, all right, to an also normal basis. We call U1, U2 up to UM for FM with, so we just ask Uj is equal to A Vj square root of lambda j for j from 1 to R. Okay, so the extension is that here this also normal set has R vectors, but we can extend it into a basis, right? You can into a basis. Okay, and the name here is U1, U2 up to UM. Okay, and so this vector is U1, this vector is U2, this vector is UR, etc. Okay, so we have that. Okay, so with that then we have A, Vi, lambda I, Ui for 1, I from 1 to R, and the 0 for 2n. Okay, so we have that result. So the action here is the situation. Okay, so this is the, so now we we have the situation here. We have V1, V2, VR plus 1, and the Vn, okay, is and also normal basis for Fn, and we have U1, U2 up to UR plus 1, UM, and also normal basis for Fm. Okay, so now we have this data. The first, this also normal basis Fn is actually eigenbasis, right? Associated with AHA. Okay, and this also normal basis for Fm. Okay, is from the action, right? A on this also normal basis. Okay, so for here, and from that we do that, and by extension. Okay, so we have a two also normal basis, one for Fn, the other for Fm. Okay, we have other Fm. Okay. Now this is very similar to the Eigen equation, except we are not using the same vectors, right? Here is Vi, this is Ui. Okay, and we know Vi, V1 and U1 are related here, right? This is the relation for all the index j from 1 to r. Okay, but there are no relations here for the rest of the basis vectors. Okay, for here V sub r plus 1 up to V sub n, actually this vectors span the null space. All right, so we know they span the null space of A and the AHA. Okay, and we have the other things here, and later on we will show that UR plus 1 up to UM span is the basis for the null space of AH and AAH. Okay, later on we will show that. Okay, but up to now we know some information of them, and we have this. Okay, and so we have actually n equations, and so we write the n equation together, right? So we have A, V1, V2, VR plus 1, Vn. Okay, and this is equal to U1, U2, UR plus 1, UM. All right, and here we have square root number 1, square root number 2, up to square root of number r. And we have 0 and the 0 and the 0. Okay? So this is equivalent to these n equations here. They are equivalent to each other. Okay. Now, so this one defined to be V, and this is defined to be U. And so because it's an also normal basis, okay, for the Fn, so that this is a unitary, n times n unitary matrix. And this is an m times m unitary matrix. And this is called, so this is defined to be sigma, right? And it's an M times n diagonal matrix. Okay? It's also diagonal because it has only non-zero values on the diagonal, even though the diagonal may be short, okay, because it's rectangular. Okay, but so it's an M times n diagonal matrix. Okay, and with so that and with R positive diagonal entries, square root number 1, square root number 2 up to square root number R. Okay, so we have that. Okay, so we have this. All right, and so now we have, so we call the R positive diagonal entries square root number 1, square root number 2, square root number R of sigma are called the singular value of A. Okay? So singular value of A are just the square root of eigenvalues of positive eigenvalues of AHA. Okay? So they are called singular values. And we have, from here, we have AV equal to U sigma. And so this is saying that A is equal to U sigma VH. Okay? If you multiply VH here from the different side, this is identity. So you have A and you have that. So this is which is called the singular value decomposition, called SVD of A. It's called the single value of A. Right, so you can see this is a rectangle matrix. This is M times N. Now you have a unitary matrix U, which is M times M. And you have a diagonal rectangle matrix M times N. And you have the N times N unitary matrix. So it's very similar to our unitary diagonalization, right? It's very similar to that, but not exactly. Okay, so we have the symmetry, and this decomposition is good for every M times M matrix. That is the crucial part. Okay, that's the crucial part there. Okay, so I will stop here, and so please read. The rest are some development of the idea, because the key idea is already there. Okay, so please read the rest of this subsection in the lecture notes. Okay, so I have to conclude my lecture in the semester, right? So I remind you, our final examination will be next Wednesday, starting at 10 a.m. sharp. Okay. Okay. So good luck for the final examination, not only for linear algebra, but for all the courses for you. Okay.